Practicing. Okay, guys. Lesson 4.5, linear approximation. Here we go. Okay. In Unit 2, we looked at the idea of local linearity. When zooming in on a function, we discovered as we zoom in on a specific piece of a function, the straight line that appears at a given point has a slope equal to the derivative. Okay, so the idea that you can zoom in on any piece of a function close enough to where it looks like a straight line. And that is what the derivative represents, because that is the slope of the tangent line. Now, equation for the tangent line at the given point was defined as f of x equals f of a plus f prime of a times x minus a. Or in other words, that is essentially your y1 plus m times x minus x1 is really what that is. And I'll write that down here in the next part. Okay, so tangent line approximation. Suppose f is differentiable function at a point x equals a. Then for values of x near the tangent line, approximation is approximately equal to, and this right, as I said, this right here, this f of x equals, I don't like that, f of a plus f prime of a times x minus a. That is the same idea as saying y equals y1 plus m times x minus x1, which that is what? That's our modified, not slope-intercept, but point slope. Because in algebra, I taught it as y minus y1. And for calc, we've modified it and moved the y1 to the other side. Okay? So that is your idea of tangent line approximation. We're going to define this expression here as the local linearization of f near a. So we're really still talking about tangent line. Okay? If you consider that point A is a fixed point, then f of a and f prime of a are constants. And you will see in this lesson L of x pop up. Okay? And they use L of x to represent linear, I want to say linear approximation is a piece that, there's lots of L's here. But they use it to represent the linear approximation when they talk about L of x. Okay, so we'll talk about that some as we go through examples. Graphically, linear approximation, delta f. So change in f is approximately f prime of a times delta x. I guess right there is that, okay, where delta f is f of a plus delta x minus f of a. So that is like the change between the two pieces, okay? I thought she was looking for gum. I'm like, gum is after lunch. Mm-hmm. No, it's the eraser.
It's in my locker somewhere. It's still in my coffee.
And normally you should be at lunch right now. Mm-hmm. Okay. The other piece that we'll be looking at is error. The error in linear approximation is just the gap between the actual curve, and I'm going to explain that here on this picture down here. So we have an error formula. Error can be calculated by the absolute value of the exact amount minus the approximation. And we talk a little bit about percentage error there, which you guys would have an idea of how to find percentage error.
Oh, yeah. Chemistry.
Yeah.
We're literally trying to figure that out.
Whether or not we do it exactly the same, we'll see. But
it's exactly the same. It's the same as physics. Yeah.
Okay, there we go. Okay, so let's look at this picture here. Let me get a different color than navy to write in. It can be shown that the best linear approximation to f near a is the tangent line approximation. Label the true value of f of x, the tangent line, and the approximation. So, what do we have here? This curve is f of x, right? Now, so if that curve represents f of x to, in general, right? So the curve represents f of x. Where is the true value of f of x? Well, specifically noting, what do they have down here?
X.
They have x marked right here. So where is f of x?
That little dot.
And I assume, I'm hoping she means
That dot.
that dot, right? Like that is the true value of f of x. It doesn't have anything to do with the tangent line or anything. That is, we take x, whatever that value is, and plug it in. That is the true or exact value. I'm trying to figure out where I want to label this. True or exact value of f of x. This is going to be a mess when I get done labeling on everything I want to label. Okay. I regret where I labeled that already. Oh well. Moving forward. Tangent line. Where's the tangent line?
The line.
That's right there. The line.
Okay. The straight line, yes. Not the curvy line. I know. No such thing, but. So I'm going to label this down low. So there's our tangent line. And now, approximation. Okay, so what is the approximation of f of x in this case is what I'll call it. So when we talk about the approximation, that is using the tangent line. And so we talk about the approximation when we look at x. X on the tangent line is going to be that point right there. So that is your linear approximation value because it's from the tangent line. And ideally you use it for very close numbers. So this is our linear approximation. Okay. Now, do I have anything else? That's what they asked us to label. Do you see E of x in there?
Yeah.
What's that E of x represent?
The graph, the name of the graph?
It's the
Error.
that space between
okay.
That.
Remember, E of x starts for error. So this right here, the distance from, okay, the distance from the exact value to the linear approximation, it is labeled as E of x, and it is your error. Okay, so that represents your error. Labeled, 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 labeled. Okay, now, if I recall correctly, I have it in my notes here, so we're definitely going to talk about it, regardless of whether we talk about much in this homework or not, but is this linear approximation going to be an overestimate or an underestimate of the actual value? And why is it an underestimate?
Because it's
Under it.
Okay, because, and so in this problem, anything on this tangent line is going to be an underestimate, right? Whether it's close or far away, it's going to be an underestimate.
Group 3, if you are in Group 3, will you please come to the middle school office? You will be leaving soon. Group 3. If you're not sure you're in Group 3, come see me in the middle school office.
We're bad.
Yes.
I think she's a very nice lady.
She is. She's very nice.
It's just very monotone when she goes over the speaker, and that's what reminds me of her.
Concave. I remember that.
Sorry, I just started writing because I'm like, I'm not going to try and fight with the intercom. So. You guys are no good for me because now I'm not going to get that image out of my head. And I love Mrs. Sanders
Do
to
you
death.
disagree?
But no, I don't. That's the thing. I can hear like the way she announces on the intercom. I can hear it. Oh my goodness. Okay.
We told that to Doc one time too.
I can hear it. I'd be half tempted to tell her because I think she'd laugh. I do.
I don't think she would.
I do.
As long as you don't use our names.
Okay.
The chance.
So you guys mentioned underestimate. Okay, it's an underestimate because the graph is concave up, so it's curved upwards, right? Okay, or bold upwards. The tangent line is below that provided graph. Okay, so you guys all appeared to understand underestimate, so I didn't feel like I need to go that much into it, but I just realized I was going to zoom in on that part when I went to do that part. That's why I was struggling so much to fit everything in.
It's okay.
Oh well.
It's fine.
Okay.
Yep.
Okay. The next page talks about procedure. I'll read through this briefly, but we all know the best way to figure out the procedure is to do it, right? Reading through it is only somewhat so helpful.
You read through this and I'm like, am I paying attention? Am I gonna retain?
Well, and I'll be honest. Do I spend a lot of time going through this part? No, on purpose, because
It's not.
it's, I'm going to give you some information. So, okay, now notice what it says here. So, if your head is spinning, which I don't feel like a lot of that first page is brand new. I mean, it all relates to tangent line. It's kind of a different way to talk about tangent line. So, we are going to be asked to write a lot of linear approximations, okay? You'll notice up here when I'm reading up there, when you need to write a linear approximation for f of x centered at a given value, and so say in this case x equals c, you need to approximate f of x at a value that is in the neighborhood of x equals c. Let's call this new value x of a and then proceed as follows. So the idea, we're picking something that is very, very close to the original value. Okay, so we will start off writing point slope equation. So we'll use the modified point slope form, for the tangent line. We'll isolate y, which the way we write it, we'll probably already have y by itself, and rename it as L of x. L of x representing linear approximation. Okay. We'll substitute our value in for a, whatever that might be. And again, this right here, guys, I talked about on the other page. This is the same idea as saying y equals y1 plus m times x minus x1. That's what we're going to be writing. Okay, it really is there. Okay, I just talked about underestimate and overestimate, didn't I? So if you need to explain whether or not L of A is an overestimate or underestimate, consider the behavior of the function in your local neighborhood. So consider, there's a reason I talked about concavity here, right? Where is your graph curved? And where is this line in respect to that? Okay. When finding error or accuracy of an approximation, use your calculator. This is that error formula. Find the absolute value of the difference between the exact amount and your approximation. The error should be stated as less than 10 to some negative power is what we're going to do, where p is the number of zeros in your result. So, for example, for an error such as 0.000147, that would be reported as error less than 10 to the negative third. Okay, and then if you need to find percentage error, there's that formula that you said was a little familiar to you. Okay, so let's look at example 2 to get us going here. The function f is twice differentiable, where f of 3 equals negative 2, f prime of 3 equals 5, and f double prime of 3 equals 1. Write the equation of the tangent line, then use the equation to find the value of f of 3.1. Okay? So, f of 3 equals negative 2. What does that tell me?
3, negative 2.
Okay.
Wait, I thought it was 2 negative. Oh, never mind. That's done. Just kidding.
Are we there?
Yep.
So we have a point at 3, negative 2. They're not ever going to say that in calculus. They always say f of 3 equals negative 2.
Mm-hmm.
What does f prime of 3 equals 5 tell me? Okay, so we know the slope at 3 Okay, or I don't know, just a slope, right? The slope of 3 is going to be, so at that same point is 5. F double prime of 3 equals 1.
The slope of the slope.
Tangent.
The speed.
I don't know.
How about,
The velocity.
Acceleration.
well, it's double,
Acceleration.
it'd be acceleration.
Ooh,
Okay,
gotcha.
how about, I have written down, it's extra. Why did they throw it in? I don't know.
Trick
Throw us
to
off.
be mean.
Well,
Okay.
that's what tricked me.
Jerks.
It's
We, you know what, Sophie, you go ahead and do that. You go ahead and multiply your answer by 1 all you want. I think it'll work out just fine for you.
Exactly.
Until they throw in a second derivative of some other number, and then we're done. Okay. Write the equation of the tangent line. So we're going to use, and I'm squeezing this in because I didn't zoom in again like I should have, but that's all right. My other pages are zoomed in. So where f of x is going to be approximately equal to L of x representing the linear approximation, and we're going to be filling in that form up above of f of a plus f prime of a times x minus a. Okay, so that equation from above what can we fill in?
everybody.
Yeah.
Yeah, that's probably.
Okay,
A is 3.
yeah, knowing here that a is 3, right?
Yeah.
Okay, so all based on that, so f of x is approximately equal to L of x. F of a, what's f of a going to be equal to?
Negative.
Yeah, negative 2.
Negative 2. Plus, what's f prime of a?
5.
Times x minus, what's a? 3. Basically, you use your point, right?
Yeah.
The 3, the negative 2, you use your slope. Now,
Do you clean up after
no, don't clean up. Usually we're going to leave it like that. Okay. Now, that was this piece right here. Write the equation of the tangent line. Then, what else did it ask me to do? Find f of 3.1. Do not go straight for the calculators. I want you to process through with me that you don't have to grab a calculator on a lot of these. I know you guys don't like me saying that, but okay, so we're going to find f of 3.1, which means we're finding L of 3.1. Fill it in. Negative 2 plus 5 times 3.1 minus 3. What is 3.1 minus 3? 0.1 for that part. So if you're a step ahead of me, what is 0.1 times 5? And negative 2 plus 0.5? Negative 1.5. Okay. And I said L, we could have also said F there, I guess. I guess in my notes I have F. I don't know that it really matters that much. We go back and forth a lot in this lesson. My screen. Okay. Now, real quick, on this graph. Okay? Thank you. I appreciate the 2-minute warning. Now, stay with me for a moment. Okay? That is a horrible place to put this. Okay. I'm just going to put mine over here because I'm zoomed in so far. We have a point at 3, negative 2, yes?
Yes.
So, and we don't really know what the graph is doing there necessarily, do we? No. Other than we know that the first derivative is 5 and the second derivative is 1. but we don't really necessarily know what the graph is going. I'm trying to think, did I draw this? I think I just drew, trying to figure out why I drew the graph the way I drew it. Okay. We know our slope is 5, yes? So the slope through the point 5 is going to be probably steeper than that. But now the idea is we found f of 3.1 to be negative 1.5. We know that f of 3 equals negative 2, yes? So there's f of 3 equals negative 2. F of 3.1, so a value slightly past that, is going to be negative 1.5 on our tangent line. Okay, that's our approximation. Now, the idea is that our graph, because of where this tangent line is, and that point is, our graph is below here somewhere. Okay, we don't exactly know where, but our graph is below here somewhere. I can't draw what I want there. Okay, so we have that point of 3, negative 2. Okay, this point would represent the one we found of 3.1 comma negative 1.5. And the idea of the actual value of 3.1 is going to be on the graph right there. Okay, we don't exactly know what that value is because it's an approximation of it. But the actual value of 3.1 is going to be whatever that is. This was our approximation. Okay, so that's the idea of what I'm trying to show you, that it puts us in the neighborhood is what you'll hear them say. Okay, so linear approximation. We're going to be using it to estimate values for f of x, provided you stay in the small neighborhood. Does this tangent line work the farther I get away from this point?
No.
No, because the farther we get away from the point, the curve's going a different direction. It doesn't really work. So it works as long as you stay, as they say, in the neighborhood. Okay? Yeah, the farther away we move, the worse the approximation comes. And this is where we're going to talk about predicting error.
Should we take
That'll
that
be next
one
page.
outside? Can we leave our stuff in here?
You have not had B lunch for